Let's look at the scatter plots for the golf data. This one shows the putting average for the 2015 data, which included over 180 players. Putting average is the average number of putts per green, so smaller is better. So you'll notice with smaller putting averages, there appear to be higher salaries. Driving average, the longer the driving average, the better. So here our higher driving averages seem also to have higher earnings. The 2015 data seem to show that the smaller the putting average, the higher the earnings, and the greater the driving average, the higher the earnings, although the relationship is not very strong for either. The data seem to support that both good drivers and good putters make more money. We need a way to measure the strength of the relationship between variables to say which has more influence on earnings. In this lesson, we're going to describe the properties of the linear correlation coefficient R, and that's going to be our measure of strength that will help us answer the golf problem. Take a deep breath before you go to the next slide if you don't like math. You do not need to know or use the formula that's about to appear, but there might be a mathy person out there who would like to see it, so I put it in the slides. All you need to know is how to interpret the correlation coefficient R when you see it. The linear correlation coefficient, or Pearson product moment correlation coefficient as it's sometimes called, is a measure of the strength and direction of a linear relation between two quantitative variables. We use the Greek letter rho to represent the population correlation coefficient and the lowercase r to represent the sample correlation coefficient. And math is case sensitive. If they use a little r, then chances are a capital R is going to represent something else later on. We represent only the formula for sample correlation coefficient below. What you need to know is the properties of the linear correlation coefficient R. First, the linear correlation coefficient is always a number between -1 and +1. If R is a +1, then a perfect positive linear relationship exists between the two variables. If R is -1, then a perfect negative linear relationship exists between the two variables. In real life data, the correlations are never perfect. The closer R is to a +1, the stronger is the evidence of positive association between the two variables. R increases as the graphs below go from left to right. So we have an R value of 0.5, a moderate relationship between those variables. A stronger relationship of R equals 0.8 is in the middle graph, and an R value of 0.89 in the last graph. So you can see the more tightly the data follow a line that goes right through them, the higher the R value is going to be. Property 5, the closer R is to -1, the stronger is the evidence of a negative association between the two variables. So we have a moderate negative correlation of -0.43 in the first graph. This next graph represents about a -0.5, a little better at -0.66, and an R value of -0.9 shows you a much stronger negative correlation. You can see the data are more tightly clustered around a line going down the screen. If R is close to 0, then that means there is little or no evidence of a linear relation between the two variables. Because the linear correlation coefficient is a measure of the strength of the linear relation, R close to 0 does not imply there's no relation at all, it just means it's not linear. So the three graphs below would all give you an R value of 0 because they're definitely not lines, but there's something going on between the data in the last two graphs. There's a curve, there's some kind of relationship, it's just not linear. Below are several sets of xy points with the correlation coefficient of x and y for each set. Note that correlation reflects the noisiness and direction of a linear relationship, but not the slope of that relationship. So the higher the number, the more tightly the data are going to be in a line, but the correlation coefficient has nothing to do with how great or small the slope of that line is. Here are some more examples. If we go down the column, we have a strong positive relationship. The middle graph is a weak positive relationship. The bottom one in the left row represents no relationship. Then we have a strong negative relationship on the top right, a moderate negative relationship in the middle, and a weak negative relationship on the bottom. In this slide, the actual R values are not given. On the left, we have another graph of a high positive correlation. Notice the points are clustered as to resemble a rising straight line with a positive slope. And you can imagine the line might go through here, something like this. The graph on the right is a low positive correlation. While the points tend to be rising, it's not clearly positive since points are not clustered on a clear straight line. You could imagine a line maybe going through here like this, but the points are not generally very close to that line, so that would be a low or weak positive correlation. Here's some more examples with negative correlations. The top left graph, the points are clustered as to resemble a falling straight line with a negative slope. So they would be tightly clustered around a straight line that would go right through the middle of the data. In the middle, we have points that tend to be falling. It is not a clearly negative relationship since points are not clustered as to show a clear straight line. There's some linear relationship here, but the points are not tightly clustered around that line. And the last graph on the bottom right shows no correlation. There's no way of determining from these points if the pattern is rising or falling. There's no evidence of a straight line in there anywhere. The linear correlation coefficient is a unitless measure of association, so the unit of measure for x and y plays no role at all in interpreting the value of R. The correlation coefficient is not resistant. Therefore, an observation that does not follow the overall pattern of the data could affect the value of the linear coefficient. You will recall from previous discussions that mean and standard deviation are two other non-resistant statistics we've looked at. Note the effect of the addition of one outlying data point on the graph and the R value. So here we have an R value of 0.86, a pretty strong positive correlation, but with the addition of this one point out here, we see that value drop to a 0.45. Now let's look at calculating and interpreting the linear coefficient. Actually, you'll use software to calculate, but once you calculate it, then you need to be able to interpret it. So again, we have more examples. We start off with a perfect positive correlation, which would be an R value of 1. And then we move to about a 0.9, and you can see that you still can see that line in there, but the points are not as tight on the line as a perfect correlation. And as the R values get closer to 0 and further from 1, you can see the spread in the points. Then we move on to a perfect negative correlation, an R of -1. And here's an R of about a -0.9. Again, you see the points begin to spread out away from the line, and an R of about -0.4 with more scatter. Graph G shows you a plot that has an R value close to 0, and notice how scattered the points are. And even though there is a curved relationship in this last graph, it would still have an R value close to 0 because remember, R tells us if there's a linear relationship. It doesn't tell us anything about any other types of relationships that might exist. Explain whether there is a positive correlation, a negative correlation, or no correlation between the sets of data in the scatter plot. In a scatter plot, as one set of values increases, if the other set tends to increase, then there is a positive correlation. If the other set tends to decrease, then there's a negative correlation. So there is a positive correlation here because as the x's go up, the y's go up. The graph below represents an R of 0. Go to the following site to enter your own data and observe what happens to the R values. So you can set the scale if you want to. I'm just going to leave it like it is. You can see it goes from -10 to +10. And you can put some points in here and tell it to show you the regression line, and your R value is over here at 0.21, so not a very good relationship. But if I put more points closer together, watch the R value go up. And as the R value increases, you can begin to see a more linear pattern to the data. And if I put an outlier way out here somewhere, watch what happens to the R value. Now let's go back to our drilling data. Determine the linear correlation coefficient of the drilling data we looked at previously. If you don't have a graphing calculator, you can go to the Schroeder site. This site lets you type in data in ordered pairs rather than having to click like I just did on the previous site. For example, you would enter 35, 5.88 and then hit enter to type the next point on a new line. After you enter all the data, hit update plot to graph the points. Stop the video while you find your own R value. The R value for this data is 0.773, which shows there is a moderately strong relationship between the depth at which drilling begins and the time it takes to drill 5 feet. The following slides tell you how to do this on the TI-84. Again, you should print those and go through it step by step as you enter your data. Now let's go back to the golf example. The graph below shows the regression line for the putting average data. The vertical axis represents earnings in millions of dollars. Putting average is on the horizontal axis, and the R value is a -0.53. So there is some relationship there. We said before it was a pretty weak one, and it is a -0.53. The graph below shows the regression line for the driving average data. The vertical axis, again, is earning in millions of dollars, and the driving average is on the horizontal axis. Here we have a value, an R value of 0.39, a very weak positive relationship, but there is a little bit of a relationship there. Although R equal -0.53 is a fairly weak correlation, it is stronger than the driving average correlation of R equal 0.39. Remember, the sign just tells you the direction of the relationship. Thus, a better putting average does seem to be more closely related to higher earnings than driving average, although the relationship doesn't seem strong enough to warrant the saying. Maybe more attention is given to putting because it occurs where everyone can watch closely, and the strokes determine the score for the hole. This may make good or bad putts more memorable than long drives. Now take Module 3, Part 2, Assessment of Learning. The password is correlation.